Hello everyone, my name is Dr. Winny Wulandari and I would like to explain about tri-column design for fractionation. So let's begin. Right, so this is a picture of the distillation column. This should be around here, so you can see that there is the height and also there's some diameter on it. Usually distillation column is quite tall, and then in each stages would be appear around here. This is also one of the types of distillation column. You can see that it is like a tower, and also there is a manhole around here. And then if you just see a little bit, the top column is quite smaller, comprised to the bottom column. And then you can see all the manhole over here. And then there's something like a vessel here, maybe condenser or a reboiler and so on. Okay, so what is fractionation? Fractionation is when we want to separate a mixture of liquid and vapor into some kind of products that we want. And then in fractionation, we determine the number of real equilibrium stages. And then now we have determined the number of real equilibrium stages by calculation for binary distillation or multi-component distillation. And then how is the unit operation? How can we design the unit operation? The unit operation is called distillation column. One of the type of fractionation is called tray column because inside the column there are tray, and then all the tray, one tray represented one stage of equilibrium distillation. So for example, in here, you have the feed, let's for example, in the middle, let's here, and then there is a feed tray, and then you can see that the liquid can going down because of the gravity, and also a little bit of perforated, and also from the bottom there are a vapor, and the vapor will vaporize up to go there, and then we understand that in each stage that would be an exchange or the mixture of the liquid and vapor will interact, and then it will result in new equilibrium based on the different the condition of temperature and pressure. So to obtain the column design, we have to determine the diameter of the column, determine the tray spacing, how much is the distance between two tray, and also to determine the configuration of the column. Okay, let's just refresh what is the tray function. Tray function is to mix vapor from the bottom and also liquid from the top in order to ensure vapor-liquid equilibrium is achieved. And after the vapor and the liquid is mixed and then the equilibrium is achieved, then the vapor should leave upwards, the vapor flow, and also the resulted liquid should flow downward. So tray function need have a good contact between the liquid and also the vapor from the bottom, but also it also need a good separation after the equilibrium is achieved. So this is a schematic of distillation column in a tray column. Here we can see this is the tower, and this is the typical of one tray, and you have see the liquid in, and then this liquid they would kind of wear like a wear like that. So some liquid will build up here, and after that it will flow that side and then go to the downcomer. But from the bottom there, you can see some vapor, and the vapor will make kind of like a froth or like a smoke there, and then it will evolve in and on the near all the sieve tray there. So in each stage, the liquid will contact with the vapor, and then the equilibrium will goes in this way, and then it will be resulted in a new composition of vapor and new composition of the liquid that gets outside of the downcomer. If we look at the inside of the equipment, it would be looks like this. This is the sieve tray. It looks like a tray. Of course. And then, of course, we have the cartridge support just to make sure that the sieve tray can be placed in that height. And you have this one is called the downcomer, when you have the liquid and then the liquid will flow downwards. And also some lip seal, of course, also liquid seal when it operated not in the atmospheric temperature. Okay, so let's have a look about the flow scheme of the tray. If this is the plate above, and this is the current plate that we're looking at, you will get the liquid from the plate above, and then this will hold into this height. And on the top of the clear liquid, you will find some froth, like kind of bubble, something like that, like a froth. And after that, the clear liquid will flow to that sides. And then when it mixes with the vapor from the bottom, it will create a froth. Froth is when you have a vapor trapped in liquid, and also you have a spray when you have a droplet of liquid which is trapped in the vapor. And after that, you will have the liquid will, of course, will flow with the new composition we would like to. And then this is called the downcomer. And then this called is a kind of calming zone over here. So this is we call it, this one is active area. What is called active area? The active area is the area where there is a interaction between the vapor from the bottom with the liquid from the top. And after that, of course, the liquid, the clear liquid will form again, and then the plate below. For this liquid flow on the tray, there are 3 types of flow. The first one is called single pass flow, like this one. So the liquid come from one side and then go to that side, and then it's gonna falling in this side. The second one is called the reverse flow, which we have a border like this. So the flow would be a little bit of reverse. And the last one is called the multi-pass flow, where we have multiple or 2 paths of the flow to this side and that side. And then let's have a look about the types of bubble trays. There are 3 common types of bubble tray. The first one is called bubble cap tray. Second one is called sieve tray or perforated tray that we usually use in the assignment. And the next one is called valve tray. The function of trays is to be able for the vaporized pass to the hole and valve. It's not too small, because it's small, then it will be trapped, and then you will have some like the pressure loss, but not too big as well. So the liquid will dripping to this side. Okay, so there's some requirement that need to use for the trays. Okay, this is the bubble cap tray, where the bubble cap tray, you have some cap, which is the vapor can goes into the inside the bubbles then, and then the liquid, it will prevent liquid whipping, or called liquid dripping, or it would be also have a good to ensure all the vapor will be kind of distributed into the liquid. This is the type, for example, the photos of a bubble cap tray. But the drawback of bubble cap tray that you will have a higher pressure drop in this area, and also it's a little bit complicated. So let's have a look about the videos.
The bubble cap tray was the most used device through the 1940s and early 1950s. An amazing number of them are still in service. The tray consists of a riser with a cap on the top. The vapor flows through the riser and around the cap and contacts the liquid as it flows across the tray. The one unique advantage of the bubble cap is that it provides positive assurance that there will be total vapor-liquid contacting without bypassing of the vapor. Their main drawbacks are due to the complex cap design. The caps present an obstruction to liquid flow, particularly in high liquid-loaded towers. Also, a large fraction of the vapor phase pressure drop is wasted, as it occurs in the reversal area between the riser and the cap, where it does not enhance the mass transfer. The labor cost of assembling the riser cap units makes these trays more expensive. The weight of these units also leads to support problems on large towers. Consequently, most new applications today are in services where a large amount of vapor must contact a relatively small amount of liquid.
Okay, so let's go the next one. Okay, so yeah, so that is the vapor flow in the bubble cap look like that, like in the videos. And then there are a number of types of caps with different design based on different manufacturer or just different type of design. The second one, so let's see, this is the sieve tray or perforated tray. So it's quite simple. You have a perforated tray and then which enable the vapor will pass through the perforated sieve, and then it will contact with the liquid. In a good condition, you will have all the vapor will contact with the liquid, will intimately contact, and then you will have a new equilibrium position, and which is ready to be separated. However, the sieve tray have some drawbacks. When you have a low vapor flow condition, then the liquid will dripping or whipping through those perforated tray. So let's have a look about the sieve tray or perforated tray.
Sieve trays have also dominated tray column design over the last 40 years. Liquid flows across the tray surface and vapor flows up through the tray holes. The area above the tray surface is the turbulent froth as the vapor and liquid mix. They are the simplest design and hence are relatively inexpensive. Vapor pressure drop is also minimal as there is no resistance to the vapor flow from valves or caps. Disadvantages include liquid weeping down through the holes and entrainment at high vapor rates. This results in a lower operating range.
Right, so for sieve tray or perforated tray, you have a quite a small window for operating, because when you have high vapor, there would be entrainment, and also when you have a low vapor, then you will have weeping. Right. Okay. The next one is called valve tray. When you have a valve like this one, at normal vapor, then the valve will kind of push up, and then vapor will goes to the liquid there, and then there would be a contact. When it has a low vapor, then the valve will just come down and then close it, so there is no weeping for the liquid. When you have a very high vapor, then it will just increase like that. So it would be looks like this. So it kind of looks like a valve tray like that. In a normal condition, the valve would be looks like this one.
Valve trays, along with sieve trays, have dominated for the last 40 years. Valve trays generally are proprietary and contain movable valve units. When the vapor rate is low, the valve partially closes and minimizes weeping by restricting the liquid flow through the tray holes. At high vapor rates, the valves deflect the vapor flow. This reduces entrainment by creating a weaker vapor jet and results in a greater operation range. The valves do contribute to vapor pressure drop, as the vapor must push the valve open.
Okay, that is the advantage and disadvantage of valve tray. Okay, let's have a look at the next one. So this is the comparison between tray types. Sieve tray, the capacity is high, efficiency also high, but entrainment moderate, pressure drop moderate, and also has a low cost, low maintenance, and low falling tendency, also low effect of corrosion. Valve tray, the capacity is high and very high. There are turn down ratio both these sides, and then the cost is 20% higher than sieve tray. It's also low to moderate maintenance for falling tendency, also for the effect of corrosion. For bubble cap tray, the capacity is moderately to high, and also turn down is excellent, good at extremely low liquid rates. The entrainment also very high, 3 times of sieve tray. The pressure drop is high, and then the cost almost 2-3 times of the cost of sieve tray. The maintenance is relatively high of those bubble cap, and also falling tendency, it will be also high. It intend to collect and trap the liquid. Effect of corrosion, of course, very high. And the last one is called the dual flow trays, very high capacity, lower than other type for the efficiency. For the turn down also low, the cost also low, and the falling tendency also low. Okay, and then also the availability of design information for sieve tray is well known. For valve tray is proprietary, so we cannot get the available. And also for dual flow tray, some information is available. So the main application is for sieve tray is when MOS column when turned down is not critical. For valve tray, usually used for MOS column, and then service when the turn down is important, and bubble cap tray when extremely low condition and also leakage must be minimized. And for dual flow tray would be when the capacity revamp, efficiency, and turn down can be sacrificed, and high folding and corrosion surfaces. Share of the market, about 25% on sieve tray, 70% of valve tray, and 5% of bubble cap and bubble cap tray, and then there's no information on dual flow tray. Okay, so let's have a look about the stable operating area of the sieve tray. Just look at that on the horizontal one is called the liquid flow rate, and also the vertical one is called the vapor flow rate. When you have a low vapor flow rate in this area, what you have is going to be, you have a whip point. Whipping when you have the liquid dripping through those perforated hole into the bottom tray. And this is not good. So this is the we cannot have the operation below the whip point or excessive point, or very low one is called the dump point, where practically all the liquid will just dripping and then flowing to the holes. If you have a low liquid flow rate and you have a vapor flow rate, what happens is your liquid will be carried over to the upper plate, to the upper tray. So it's called the excessive entrainment. Or if you have a quite moderate liquid rate, also very high flow rate, it will have entrainment flooding. Or if you have higher flow rate, also higher, or maybe a very high liquid flow rate, you will also have a flooding to the downcomer. So in the sense that the area of satisfactory operation should lie in this region, so it doesn't have any entrainment, both excessive entrainment flooding or downcomer flooding. It doesn't have whip point, it doesn't have excessive whipping and dump point. Okay, so how to prevent all of those unwanted things in the operation? So first one, let's have a look about the effect of liquid to vapor in flooding mechanism. If this is the pressure, which is looking at the gas pressure or the vapor pressure, and then on the vertical one is called the liquid to vapor ratio. If you have a small one here, we have a small liquid and small pressure. You have a spray entrainment. If you have over here, you call it the entrainment or Duncommon flood. And if you have high liquid to volume ratio and pressure, you will have Duncommon flood as well. Okay, let's have a look about flooding and entrainment.
A flooding condition occurs when the froth level approaches the tray above. Flooding occurs at high vapor rates and results in a significantly lower efficiency. At these high vapor rates, the vapor carries much of the liquid up with it to the next tray. This recycling of the liquid is called entrainment. Entrainment mixes the stages together and reduces the countercurrent effect of the column. Flooded columns are also difficult, if not impossible, to control, as the separation performance will decrease dramatically.
Okay. Okay, so the flow of vapor and liquid at the entrenchment and stripping also may be different on the top side and also to the bottom side also may be different. So when we calculate later on the column dimension on enriching and stripping also will differ as well. The top column design will be presented by the top tray of the column in the first tray there. So you have the composition, you have the temperature and pressure. So then you will find the properties, and then you can calculate the column design there. For the bottom product, or for the bottom column design is presented by the bottom tray of the column. Okay, so tray design again is based on the vapor and the liquid flow between trays. This is from the upper tray or the tray teratas, and also this one, the lower tray. Okay, so from the exact calculation, we can get the vapor and liquid flow, which is in the molar rate. And for a tray column design, we need mass rate and volumetric rate. Thus, we need density data and the molecular weight for each molecule in the vapor and the liquid, which is a function of temperature and pressure. So the first step, you need to write the spreadsheet or calculation data sheet as below. The calculation data sheet will comprise vapor condition and the liquid condition. Sorry, this is the liquid and it's the vapor. So the molar rate that you get it from the calculation, you can write it LM and VM, and then change it into later on to the mass rate in kilograms second, also volumetric rate with cubic meter per second by finding the molecule weight, it's not rate, yeah, and also the density. And then write it for a top tray and also the bottom tray. And then you can get the density, also the molecular weight, also the volumetric rate, maybe data from HYSYS. Okay, so let's have a look about how we design a tray column for fractionation using perforated or sieve tray column with the references from CNOT RK, Chemical Engineering Volume 6, GM, Coulson and Richardson, an Introduction to Chemical Engineering Design, published by Pergamon Press, 1983, for the design methods, and from Kister, HJSZ, Distillation Operation, published by McGraw-Hill Publishing Company, 1990, which contains picture and graph. Right, so let's define the area definition in the tray column. If you look at this area here, there are some area that is fulfilled with all the liquids, and this area is also fulfilled with the flooding liquid, which is coming out from the tray. So this area is not used for a contact between the liquid and the vapor. So then let's have a look this one. So all of the area is called the column area, this one here. The over here is called the down camera area, because in down camera area, you don't have any vapor here. It's just like the liquid is pouring. And then this is the net area on the tray, but you also have active area, because in this side is only liquid coming in. So again, there is no vapor. So the active area would be around this area. And then, of course, because there is a hole there, so you can also define the whole area. Okay, so the column area AC, down camera area AD, net area AN, active area AA, and whole area AH. Right, so because we have to prevent from flooding, from extensive entrainment, from weeping, from down-camera backup, also from coning, so we have to check the sieve plate performance diagram. A maximum vapor velocity will contribute to flooding condition, but a high efficiency of tray also will result in high vapor velocity. So for good vapor velocity, the convention is around 70 to 85% of flooding velocity. And then so we have to determine the flooding velocity, which is this will be used to predict the column diameter. So that, and then the distillation column design is actually, we design the top one, the top column diameter, also the bottom column diameter. If the top and column diameter is not much difference, it's not too differ, then you can use the larger one and then use both for both side, top and the bottom. If the diameter on the top and bottom differ significantly, then you have to choose different diameter between the top and the bottom column. Okay, how to calculate or how to predict flooding velocity prediction, flooding velocity, or UF? We're going to use on the basis of net area AN. So UF is defined by K1 value, square root of rho L minus rho V over rho V. So rho L is the density of the liquid, rho V is the density of the vapor, and K1 is a constant which is determined from a vector which is called FLV, and then we check it in the K1 diagram. FLV is defined as LW over VW, square root of rho V over rho L, which is here you also can get the LV and VP, and K1 must be corrected if the whole active area is different than 0.01, and also if the liquid surface tension is different with that you is the basis. As the basis, hole size should be less than 6.5 millimeter. The wear length should be less than 15% of plate spacing. Non-foaming system, hole area to active area ratio should be larger than 0.1, and liquid surface tension should be 0.02 Newton per meter. So if it is different, then K1 must be corrected. So when we can calculate the K1, also when we can calculate the FLV, and then we determine the plate spacing, you can determine which spacing that you will use. Is it 0.15 meter or up to 0.19 meter? And then go to the side, you will get the value of K1. And then if the K1 must be corrected, then just get the corrected. And this K1 will be used to predict the flooding velocity in the previous slide. Okay, so the calculation will be based on the net area. Once you know the flooding velocity, you can get the maximum velocity that you want, and also you can calculate the AD or the area. Then you can get the diameter. You can determine estimate the volumetric flow rate, and then you can estimate with the height, and then you can get also the area and then the diameter. Okay. Oh, sorry, I haven't translated this one. So for the flow rate of the liquid in the tray is actually influenced by the flow of the liquid and also the diameter of the tray. This is a type for the cross flow single pass or single pass over here. So this is the liquid flow rate on the vertical one, and this one is the diameter column. So once you know your diameter column from 1.0 to 2.0, 3.0, and so on, and then you find your liquid flow rate, and then you can see the your area should be single pass or should be double pass or should be reverse flow. Usually we try to find it maybe around cross flow should be good. So when you have the upper diameter or lower diameter, if it's not much different, let's say 1 meters and 1.05 meters, not much different, then you can just make sure that the higher one is the diameter. Okay, so that is called the professional plate design. When you have the diameter, you have the tray spacing, you know the number of stages, then you know the total height of the column. But then the dynamic behavior must be checked. What are the dynamic behavior that should be checked? The first one is called weeping condition. Over here, when you have low flow rate. The second one is plate pressure drop. The third one is downcomer liquid backup, which is froth height and downcomer residence time. And the fourth one is entrainment. What is the first one? Let's have a look about weeping. Weeping is a liquid leakage from the plate holes. Lowest vapor velocity is at its weep point, and the whole area must be chosen so that low vapor velocity must be higher than velocity at weep point. There is a testing on the weeping. You need to test it. So the lowest vapor velocity at weep point, and we have to also check the low vapor velocity must be higher than velocity at weep point, because if it is less, then the liquid will weep. The second one is called the pressure drop. The maximum pressure drop per plate is 150 millimeter liquid, and the maximum total pressure drop should be a maximum 10% of operating pressure. And there are a number of pressure drop that incorporated in the tray. Which the pressure drop total would be the pressure drop of the downcomer plus pressure drop of the wear, the pressure drop of the overwear, and also the pressure drop of the residence time. Okay, and now let's have a look about downcomer liquid backup, which is the liquid just flowing to the downcomer without contacting to the vapor. The chosen downcomer area and tray spacing must not cause liquid and wear height is less than the height of the upper tray. And then for froth height, the height of liquid downcomer must not be higher than 0.5 multiplied with plate spacing and wear height. And downcomer residence time should be minimum 3 seconds. And for entrainment, which is when you have a liquid which is carried out to the next plate, the maximum it should be 10%. And also there are some calculation for that one in the book. Okay, so there you are. So you have the, again, area definition, and you have the wear. This is the length of the wear. This is the height of the wear. And then you have the tray spacing like this one. And also you have the height of the overwear, height of the wear, height of the AP, the height of the backup there, and also the length, the tray spacing. Okay, so in summary, the algorithm to determine the stable operating tray, the first one you have to calculate FLV and then determine the tray spacing, find the K1, and then check the correction needed and calculate the correction of the K1. When we calculate the K1, we will find the flooding velocity UF. and determine the flooding facility. Is it 70%? Is it any 85%? And calculate the max vapor velocity. From this one, you can calculate the net area, the downcomer, the column area, active area, and hole area. So you can calculate all the area. And when you have the area, you can just calculate the diameter there. And also the hole diameter and wear height should be also calculation. This will result in professional design. So do modification if you need to check and adjust the top and bottom side. The professional blade design or modify should be tested. So the design testing must be done for top and bottom trays, even it use the same dimension and configuration. And for the top side, again, use the liquid and vapor flow on the top side, and bottom side using liquid and vapor flow of the lowest one or the stripping. And then again, there are 3 types of testing. So with whipping, is it pressure drop compliant? Is there any downcomer backup, or is there any excessive liquid entrainment? Okay, I think if you pass, then all design may be accepted. But if the test is not passed, then you have to change the design, maybe change the whole area, or change the percent flooding, or checking all the parameters that you have defined. And then, of course, the changes in the design will influence the other dynamics, so the design must not be passed in the testing. Okay, good luck for your assignment. Tray assignment is going to be a group assignment, of course, and also let's have fun and try to design the distillation column. So I'll see you again next time. Okay, so I should finish this the calculation or the presentation, and thank you for listening.